Something else that you may have noticed in the foregoing description of the model is that the model is deterministic. It will always predict the same y hat for any given x. In general, sample data is unlikely to be completely deterministic. There'll always be fluctuations and measurement noise. Moreover, we might wonder where our residuals are coming from. If our model was perfectly correct, then all of the answers would be right. One strategy to deal with this problem is to distinguish the modelled behaviour from the uncertainty. We separate them out as two different contributions to the measured values. We sort of imagine that the model is correct as far as it goes, but it's incomplete. There are aspects of the results that are not included in the model. It's possible to apply this kind of approach to any model. It's not restricted to the linear case. To encompass this, we add an extra term to the model. This is the error term, so that it looks like this. The error term, epsilon, captures all the possible deviations between the predicted values and the actual observations. Epsilon here encompasses a multitude of sins. These include model specification errors, that is to say, errors arising from differences between reality and our model. People often distinguish two different kinds here. One are approximation errors. These are errors arising because of some mismatch between the functional form of the model, in this case linear, and the behaviour. There are things that the true system is doing that cannot be captured by the shape of the model. The other set of errors that are often distinguished are estimation errors. These are aspects of the behaviour that crops up in the data that could have been captured by the functional form of the model, but were not because the parameters chosen were in some way wrong. Another class of errors that is kind of rolled up in epsilon in our current formulation is irreducible errors. These are errors that are due to natural variation in the world, either variability in the population or influences that can't be captured by measurements, or just general noise. The distinctions between all of these different kinds of errors, these sources of mismatch and these contributions to the noise, these are really important. For example, if the true behaviour was sinusoidal, and we were attempting to model it with a linear model, we probably wouldn't do very well. So the error term would be mopping up an awful lot of approximation error behaviour. However, for the time being, we're just going to gloss over all of these differences and consider everything to belong to a single error contribution, epsilon. Not only that, we're going to just vaguely hand wave towards the central limit theorem and make the assumption that our error term is Gaussian distributed, and that all of the errors on different samples are independent. So we can express our epsilon like this, is distributed normally with mean zero and some variance sigma squared. We say mean zero because we assume that all of the constant offset in the model will have been mopped up by some intercept term. This new formulation of the model with a normally distributed error term is no longer deterministic. The output y is now a random variable, conditioned on x and parameterized by w. Y is also distributed as a Gaussian. We can express this like this. Equivalently, we can formulate this in these terms. This is the standard formulation of a Gaussian distribution. Because we assumed that the error terms were all independent, the probability of the entire training set can be expressed just as the product of the probabilities of the individual examples. This is a probability of y expressed in terms of x and w. But y and x are fixed. We have the data. That's the actual training set. We can re-express this probability given fixed x and y as a function of w. This is not a probability because w is not a random variable, at least not in a standard frequentist interpretation. Instead, we call it a likelihood. The interpretation of the likelihood is how likely is it that we would have seen the observations x and y, which we did in fact see, if w was this particular value. We can choose as our criterion for what constitutes the right value of w to be that for which the likelihood of what we saw was as high as it possibly could be. It's worth bearing in mind that this does not mean necessarily that it is very likely. The observations could be really unlikely for any value of w. It's just that under any other value of w, they'd be even more unlikely. Given this formulation, the value of the weights that we're looking for, w star, is the value that maximizes this likelihood expression. Now, likelihoods, probabilities, are values in the interval from 0 to 1. If you take the product of a large number of these, they will become rapidly very, very small and tend to be numerically unstable. So for this reason, it's pretty standard practice to take logarithms instead. An important property in maximization and minimization problems is that there are a large number of transformations that you can apply to a function which will not move the maxima and minima. The actual maximum or minimum value itself will change, but it will occur for the same value of the arguments. So for example, if you add a constant offset to a function, that does not move the optima. If you multiply by any constant, that again does not move the optima. And in fact, application of any monotonically non-decreasing function will not move the optima. So the maximum of the likelihood function will occur in the same place as the maximum of the log likelihood. Taking the log also has the additional advantage of cancelling out the exponential which occurs in the expression for the Gaussian distribution. So let's have a look at this log likelihood expression. Well, taking the logarithm, we first convert the product into a sum. If we look at this expression inside the brackets, 1 over root 2 pi sigma, that's just a constant factor which can move outside of the logarithm as a constant offset. This exponentiation term in the middle, that will disappear, and the exponent will just become a factor in the expression. So we wind up with a summation that looks like this. Again, that initial log 1 over root 2 pi sigma term is just a constant, and we can move it outside of the summation. Similarly, the divisor of 2 sigma squared is also a constant, and again, we can move that outside of the summation. We wind up with an expression like this. Both the factors outside the sum are constants. The factor inside the summation, the yi minus xi dot w squared, that is just the squared residual for example I, and so the summation itself is just the sum of squared residuals. We can rewrite the expression like this, replacing the constants with just letters for simplification, and the sum of the squared residuals as this term y minus xw squared, which is the sum of the squared residuals that we defined earlier on. We've already noted that optimization is unchanged by any constant offset or multiplication by a positive constant. Negation flips the optimization, so it will turn maxima into minima and minima into maxima. So we can get rid of both of the constants, but one of them is negative, so we have to negate. We can see then that the optimal w star, occurs at the argmax of a minus b y minus xw squared, which is the same as the argmax of minus y minus xw squared, which is the same as the argmin of y minus xw squared, which is exactly the expression that we optimized when dealing with the geometric interpretation. As a result, we know that the optimum must be in the same place. We've already demonstrated that the argmin of y minus xw squared is at x transpose x inverse x transpose y. This is the big reveal of ordinary least squares regression. Least squares estimation is exactly equivalent to maximizing the likelihood of the parameters under the assumption of independent, identically distributed Gaussian noise. This provides some of the motivation for using this loss function in the first place beyond mere mathematical convenience, because the Gaussian noise model is often not a terrible model of our errors and uncertainty thanks to the central limit theorem. It's worth noting that when we derived ordinary least squares, we didn't have to make an explicit assumption about the distribution of errors and noise. Instead, we just made the assumption that the sum of squared errors was a useful distance metric. So it may be reasonable to apply least squares regression in cases where the Gaussian noise model fails, but it's worth bearing in mind that if the true noise distribution is very different from Gaussian, in particular if it is asymmetric, then that may mean that the distance metric is not a good one and the model fit may be very poor.